and strut, let's bring out Heather. Slides.
Sarah, I don't know. I don't know where all the particle detectors went. Yes, I had them in the lab. No, they're not there anymore. Okay, I'll come up with some other solution. Oh, look, a whole room full of particle detectors. Each of you is a particle detector. It's true. In fact, you have two dedicated ones, your eyes. Now, how does this thing work? That interrupts the flow of my talk a little bit. Okay, down for forward. Thank you. Okay, you have two dedicated ones, your eyes. The human eye is capable of seeing individual photons, quanta of light. Let me tell you a little bit about how this works. So at the back of your eye, there are two photoreceptive cells called rods and cones. Within these cells are proteins called opsins that convert the energy from photons to an electrochemical signal. At the heart of these proteins is a molecule called retinol. Now, retinol comes in two different possible configurations. There's the one I show here on the left, this 11-cis retinol, and the one on the right, all-trans retinol. This one on the left is the state that it's in when you're not seeing anything, when you close your eyes, when it's totally black. And the one on the right is what signals to your brain that there's a photon, that there's some light that you see, that's some color. But there's an energy barrier between them. So, like all molecules, retinol is a collection of heavy nuclei that are surrounded by clouds of electron probability called molecular orbitals. On this plot, I've shown two different molecular orbitals of the 11-cis configuration. There's this one here, which is a lower energy state, and there's the one on top, which is a higher energy state. So, like me in the morning, electrons are lazy. So they prefer to be in the lowest energy state possible. That means that the electron lives here. But if given a little bit of energy, it's able to be excited into the next lowest state. It can get this energy from a photon. In this case, for retinol, the energy of the photon that gets it, that difference between these two molecular orbitals, corresponds to the visible range of light. The way that you are able to see different colors is really interesting. That is because you have the same molecule, same molecular orbitals, but the energy difference between them is changed slightly by the shape of the protein, that opsin protein around the molecule. So with that extra energy, the molecule is able to change its configuration. It's able to rearrange itself into that all-trans configuration. And the electron then lives there. And that, how this works is that the configuration change, that change in the shape, pushes on the surrounding protein, causing that surrounding protein to change shape, which then sets off the electrochemical change that lets you see. So why is a nuclear physicist up here telling you about your own eyes? This is because the reason you're able to see has to do with a fundamental principle of physical reality, and that's the four fundamental forces and interaction. So what property is it that allows that electron in the molecular orbitals of the retinol to absorb a photon at all? Like, why does it do it? So electrons have something called electric charge. Electrons have a negative charge. Other particles, like a positron, which is an anti-electron, have positive charge, and some have no electric charge at all. When you put something with an electric charge in an electric field, it feels a force and accelerates. The electric charge quantifies the strength of this force, how quickly it moves through the field. So light is an oscillating wave of electric and magnetic fields. As the wave goes past, you can see that the electron, because it has an electric charge, feels some force that changes as a function of time. Because there's this interaction, energy can be exchanged. The light can transfer energy to the electron or vice versa. And because quantum mechanics tells us that energy is quantized, this corresponds to the electron absorbing or emitting photons of light. So let me ask you a question, see if you're paying attention. If electrons had no charge, let's say magically my body still held together, which it wouldn't, but let's say it did, would you still be able to see light? Raise your hands if you think you would. Okay, pretty confident in your decisions here. Okay, what if your electrons all still had a negative charge, exactly the same, but there was a different wave that was oscillating, an oscillation of different fields other than electromagnetic ones? Would you be able to see those? Okay, I tricked you all a little there at the end because some of you raised your hands. Sucha, I think I might want to have an actual conversation with you after this about the physics. In neither case, in a simple form, would you be able to see those in these cases? And that's because that fundamental interaction would be missing. There's not that electromagnetic interaction allowing you to see that particle. So as a nuclear physicist, I study a wide range of particles. This is a plot kind of showing all the particles we know of, the classes of particles, and how they interact with each other. So here we have leptons, which are the charged leptons and neutrinos. We have bosons, weak boson, photon, gluons, quarks, which make up nuclei, neutrons, protons, and the Higgs, which gives things mass. So this is the force we were just talking about, the electromagnetic force. It makes up almost every force you experience day to day. It's why my hand doesn't go through this table right now. It's why radios, generators, and particle accelerators work. But it's not everything. But it is most of what we experience. So anything with a charge can interact with photons because of this electromagnetic interaction, and can also interact with each other via photons. This is not only how many things in our world work, cell phones, etc., it's also how I detect most charged particles in the lab. There's many ways of doing this, but one that's very common is a scintillation detector. This is used in many particle physics experiments. And fundamentally, what you're doing is you're trying to capture energy from a charged particle and convert it into a signal that you can measure. So the way this is done requires that electromagnetic interaction. So when the electron is incident on some material, it passes through. That electron, or some other charged particle could be here, interact with the electrons in the material. They're able to interact by an exchange of photons, as I just talked about, and that excites some of the electrons in the material. This is what's shown on the left. They then vibrate around a little bit, lose some energy, and then they fall back down to their lazy ground state, releasing a photon, which we can then see and measure. What I actually do is similar in that fundamental principle, but totally different in practice. What I do is something called cyclotron radiation emission spectroscopy, which is fancy talk for I listen in on electrons using microwaves. Instead of having a microwave oven, which is a resonant cavity, I have long microwave tubes called waveguides. And when I put that electron in a magnetic field, it starts going in little circles. And it releases light because, as I said, electrons, they're interacting with a magnetic field, they can release light, and that light propagates down the waveguide, and I measure it. But it still relies on that fundamental electromagnetic interaction. Okay, so we can detect all charged particles. Congratulations to us. What about these guys over here, though, the neutrinos? As you can see, there's no line connecting them to photons. This means that they don't interact electromagnetically. They're fundamental particles that are neutral. They have zero electric charge. This means that they don't interact very strongly with most of what we experience. They pass straight through your eyes, you don't see them. They go straight through your body and they don't hurt you. They go straight through the very earth. Right now, this room is literally full of billions of neutrinos that you can neither see nor feel. Some of them are from the beginning of the universe, before even the earliest light that we're able to see. So how do we detect these little ghosts? So if you look at this, you'll notice that even though they don't interact electromagnetically, they do interact with one of the other fundamental forces, the weak nuclear force. This means that if a neutrino gets close to a nucleus, which is very small compared to an electron orbital, there's a very small chance it will interact with one of the particles in that nucleus. Specifically, as an example, it could interact with one of the quarks inside of a neutron, changing that one of those quarks to a different kind of quark, making that neutron become a proton and releasing an electron in the process. That electron has an electric charge, so we can now measure it. So we can now detect basically everything. I haven't told you about the strong force. We can see things interact via the strong force by an exchange of gluons. But what if there was something that didn't interact with any of these three forces? It had no electric charge, so we couldn't see it interact electromagnetically. It had no flavor, which means it wouldn't interact via that weak nuclear force. And it had no color charge, which means it doesn't interact with that third one, the strong force I didn't talk about. How would we ever know it was there? So most physicists think that such a thing does exist, and we call it dark matter. We haven't seen it with any of our detectors to date, even though we're trying very hard, which means that if it interacts with all of these other forces, it does so very, very weakly. But we do see its fingerprint on other galaxies, because like other forms of matter and energy, it curves space-time around it. This is the fourth fundamental interaction. Gray is kicking me off. Thank you for listening to my talk.
So you may see there's these cards over here. Funny story. I've done this before, and you hold up the cards. And I was at a talk where someone's talk was going very long. And I held up the end, I did 10, then 5, then 1, then end, and they just kept talking. So I wrote a minus sign in front of the 1, -1, and this doesn't help because the person doesn't think that you're going to be using negative numbers. And so he started going off topic. He's like, well, look, I've got plenty of time. Don't do that. All right, did you find him? There he is. All right. Please, Noah, wow them. Oh, no, you've got your thing. Great. Yes. All right.
Ladies and gentlemen, Professor Gray. The nature of dark matter, it's in our hands. It's in our hearts. It's in the code of life itself. But to see that, I'm going to need a helping hand. Please, if you're right-handed, raise your right hand. Okay. Thank you. And if you're left-handed, please raise your left hand. Thank you. She's paid to do that. Okay. Thank you. Thank you. And if you can't tell your left from your right, just raise them on both. All right. Okay. My son is 3. And he loves this trick. He puts his right shoe on his left foot, his left shoe on his right foot, and he looks at me like I'm the one who's mixed up. Looking out, I see some of you are closer to his age than to mine. You may have met earlier Professor Gray, and maybe you can see some flecks in mine too. In the old days, when we were your age, at places like this, at times like this, we would stop before getting started, face the flag, put our hand over our heart, and repeat after me. You know this story, right? Maybe they still do it. It's a special occasion, right? We used to do it every day, right? The good old days. But which hand? And why? The code of life starts with a cat. I didn't mean to break it to you like that. The code of life starts each gene with the bases CAT. That's the Fred Astaire strand. The ginger strand does every base that Fred does, but backwards and in heels. She rolls down the window and she starts to say, well, Fred says it starts with a cat. She rolls down the window and starts to say, it's all about that GTA. For which is right and why? The nature of dark matter. It's in our hands, it's in our hearts, it's in the code of life itself. But to see that, we need to do something that gets harder with age. We need to look in the mirror and reflect on what we see. Maybe a brave soul can raise a hand and come join us here on the stage. Please, ladies, a hand for our brave soul. Welcome. Oh, please, oh, it's okay. We'll share. For the lovely people, would you please state your name and the name of the place you call home?
I'm Amrita. I'm from Utah.
Welcome, Amrita. Okay, there we go. And is it, you click it is on?
Is it on?
It's on,
Oh.
okay. Ladies and gentlemen, Amrita from Utah. Amrita, let us be each other's mirror.
Okay.
When I move, you move. When you move, I move. But maybe we first start with a snap. Everybody. Thank you. Let's make some dark matter. We've been here long enough. Time is short. How about you switched hands? Okay.
Yeah.
So we're snapping, right? We're snapping.
Right-handed as
I remember.
you know.
I was
Yeah,
expecting you to stay,
exactly.
and you did what you did.
That's why you asked, right?
And it surprised me when you did exactly as I expected. Okay, so we got left. We're mirroring each other. We're looking in the mirror, and we're listening to the sounds, but we're tuning them out. Because we're about to put 1 and 3. Hey, stop that. We're going to take 1 and 3, and we're going to make dark matter. He said. So you're going to stay still. Okay, I'm approaching. It could go this way, it could go that way. We'll go back and forth. But the picture is like that. Or like that. Or like that. And the law says if it's not forbidden, it's required. And therefore it's neither, and it's both. It's dark matter. Ladies and gentlemen, Amrita from Utah. Let me show you what you just saw. Physics is like magic, but where the magician is desperate for you to know his trick. It's a strange business. But we do it for you. These 700 physicists, every proposal we write, every talk we give, somewhere in the fine print, somewhere on the last page, we say, you know, this is all about the future generation. We're sacrificing ourselves. We're traveling to places like Seattle. We're looking at Mount Rainier and sipping lattes. And we do it all for you. There's something to it. But let me first look. In my right hand, like a magician, in my right hand, normal antimatter. Normal antimatter. In my left hand, normal matter. And if we bring them together, what happens? I heard it, annihilation. Is there another way to say it? Someone on the third row? Destruction. Like the Vatican and angels and demons. I read it for tonight. I researched. But what if we look through the looking glass? And our left paired with their right, and our right with their left, you know, bouncing back and forth as you do. Then, instead of light energy in a flash, we get dark matter that lasts. The universe is like us. It remembers the past and hopes for the future, but not vice versa. It's made of matter and not antimatter, for the most part. And the universe has a handedness. The force that makes the sun shine, that makes the bomb go boom, that makes the Earth's core stay warm. It feels left-handed matter right-handed antimatter and not vice versa. Right hand over here. Right hand if you're right hand. Fred and not Ginger. What's the picture? There was a time before time. There was a place before space. When the universe knew not left from right, matter from antimatter, past from future. And then there became what we all are now, such as we are. Normal antimatter, mirror matter, mirror matter, normal antimatter. And this, ladies and gentlemen, as we mentioned, is the dark matter, but more importantly, it's the Big Bang, the beginning of it all. It could have been the other way. We could have been antimatter than matter. We could have been right hand rather than left hand. But like Fred and Ginger, when one starts to lead, there's nothing left over for the other to make. They say, hey, let's just make it work. So I end as we began. The nature of dark matter is in our hands. It's in our hearts. It's in the code of life itself. What we do with it is up to us.
Thank you very much. It's the most poetic physics I have ever heard in my life. We'll see.
I'll take that as a compliment.
Yeah, we'll see what we'll see what the next will bring us. So, Jorge.
Oh, thank you. Need to turn it off. Is everybody off? There's an echo, I think. Okay. Anyway, so nobody told me I had to be funny, so sorry in advance. I don't know. That was a trick here. So, but yeah, after a great, what do you call that? A monologue poetry slam. Well, you'll hear about neutrinos and why they are my favorite particles, why they are really cool, and why they are called the ghost light particles. Can I have the? Yeah, thanks. Right now. Okay, thanks. Yeah, so there you go. Okay, so before I start, I want to introduce you the particle protagonists of my talk. I'm going to do it in this way. So you have two axes. The horizontal axis corresponds to the mass, which is related to the weight of the particle. The more you go to your right, the heavier the particle is. And on the y-axis is the number of results that you get when you Google the names of the particles. So the higher you go, the say more famous these particles are. So first of all, we have the proton, which is represented by the letter P. The proton is somewhat famous. It lives in the nucleus of the atom. It is very heavy, so that's why it's far to your right, and it's a charged particle, so it has a positive charge. We then have the photon, represented by the letter gamma. So the photon is the particle the particle of light. So this is what we see with our eyes. This is what we see with telescopes. Photons are massless. That's why they're at the beginning of the horizontal axis. And these particles are neutral, meaning that they have no charge. And then we have the electrons, represented by the letter E. These are super famous because these are the carrier of electricity. And they're not very heavy. They're about 100 times lighter than a proton. And they are charged. They have a negative charge. So now let's move on. Imagine that you get a letter and it says, "Dear radioactive people." Maybe you would imagine Mr. Burns from The Simpsons. But this is happening in real life. And this is a letter that this dude, Austrian physicist Wolfgang Pauli, sent because he couldn't attend a conference, and starts his letter with "Dear radioactive ladies and gentlemen." So there was a problem at the time in which there was missing energy in the decay of certain nuclei, certain atomic nuclei. There was energy that couldn't be accounted for. So there were two solutions to that. One of them is that energy is not conserved, which would be very bad for physics. This, there are centers of physics telling you energy is conserved, there's conservation of energy. The other option is that there is a particle, a neutral particle, that is carrying away this energy. And this is what Pauli proposed. And this particle was discovered in 1956 in an experiment that actually started here in Washington State at the Hanford site, but then later moved on to another place. But they found this particle, and this particle is the neutrino. So neutrino is represented by the letter nu, the Greek letter nu. It's a very weird particle. It's not very famous. It will be the focus of my talk here. And it's a neutral particle, meaning that it has no charge. So, and it's going to be represented by this nu icon. So now, what are neutrinos? Neutrinos, as I mentioned, they are small, neutrally charged particles. Their name literally means small neutral one in Italian, and their name was given to them by the Italian physicist, Italian-American physicist Enrico Fermi. So neutrinos are about 1,000 times smaller than electrons. And as I mentioned, they are neutrally charged, which means that imagine if you have a magnet and a pair of charged plates. A charged particle like an electron would get deflected when it goes to those, both of those. On the other hand, neutral particles like neutrinos, they don't care. They just go undeflected because they are neutrally charged. This will be important for the last part of my talk, so keep this in mind. And then finally, they are very common particles in our universe. They are produced on the Earth, near the Earth, and far from the Earth. For example, every 10 seconds, every second 10 neutrinos are emitted by a banana. Yeah, by a banana. So the results of solar neutrinos, about 65 million of these guys pass through your thumbnail every second. And then you might be wondering, why aren't they famous? They are everywhere. We have an abundant number of them, but we don't see them. Why is that? Well, the reason is that neutrinos are antisocial, which if you translate it to particle physics means that they barely interact. And if you're wondering what interaction means, well, just go to Heather's talk. I'm just gonna give the nutshell here. So interact literally means what you're thinking of. So imagine two particles coming towards each other. When particles interact means that they affect each other somehow. It can be in the way of changing each other's direction, as you can see here. More commonly, two particles come into each other and they rip each other apart, and they release their energy in, for example, heat or light. Neutrinos, on the other hand, most of the time, they do this. They don't care. They're antisocial. Sometimes they interact. Otherwise, we wouldn't be able to detect them. So again, to give you a more like an analogy in real life of what small low interacting particles mean, which is neutrinos, imagine a flashlight and a wall. So the flashlight, you turn it on, you see the light coming, it stops on the wall, right? And that's because photons, which are particles of light, immediately interact. So photons are highly interacting particles. Now, imagine an electron, it comes to the wall. Electrons will penetrate the wall by a few inches. And that's because electrons are medium interacting particles. So they will come and they will interact with the atoms inside the wall, and then they will disappear in other forms of energy. On the other hand, neutrinos, they don't care. They just go through because they are antisocial, or they are low interacting particles. In fact, it'll take about 5.9 trillion miles of lead, which corresponds to 1 light year, which is the distance that light travels in a year, to stop one of these neutrinos. And this is what I mean when I say that neutrinos are low interacting particles. And now, this is the reason why we call these guys the ghost-like particles. And now you might be wondering, why do we care about them? What's the deal with them? And somebody already wrote an article about this. Why do we want to find neutrinos anyway? They are hard to detect, but scientists are obsessed with doing so. And to be honest, we're obsessed. And I'm going to tell you why. So this is not an exhaustive list of why we care about them. So one of the reasons we care about them is that we can study astrophysical objects with places that we cannot use telescopes. I'll talk about more about that later. The other is that we know that there is more matter than antimatter in the universe, and that's one of the reasons we all exist. But we don't know why, and neutrinos might have the answer to this question. And then finally, maybe it's just out of shame. There is so much of them. They are so abundant, and we don't know anything about them. So maybe that's why we are obsessed about them. But again, I'm just gonna, for the sake of time, and because this was my PhD dissertation, actually, I'm gonna tell you about studying neutrinos with astrophysical objects. So maybe some of you have seen the image of recently released by the James Webb Space Telescope, or JWST. So here's an image of the Carina Nebula. This was observed with a telescope, but there are some places in the universe that we cannot observe with telescopes. Why? Well, imagine you have an astrophysical object billions and billions of light years away. So these are huge distances. These astrophysical objects will emit particles. One of them will be protons, which are charged. They will get deflected by magnetic fields. They will not reach the Earth. Then you have photons. Photons will interact because they are highly interacting particles and disappear and not reach the Earth. And then you have neutrinos. Neutrinos will go through and they might interact with the Earth. And that's why we need really big detectors. And you might be wondering why I have the Antarctica there. Well, it's because we are so obsessed with neutrinos that we went to Antarctica, we drill into the ice, and we put detectors there. This is the IceCube telescope. Yes, it's the IceCube telescope, and it's a really big experiment. The scale of this is about 3 Eiffel Towers if you stack them to each other. So we drill down to 1.5 kilometers, or between 1.5 and 2.5 kilometers. We install detectors, and we want those to detect neutrinos. This is about 5 times the height of the Space Needle for people here in Seattle. So now, finally, I just want to conclude with neutrinos are really cool. And hopefully I convince you why you should care about them and why they are called the ghost light particles. Thanks.
Thank you, Jorge. Excellent. Okay. So Julia, it's often said last but not least. This is particularly applicable in this case because they don't call it the Small Hadron Collider, do they?
Sure don't.
Okay. Have you got your thing working?
I don't have.
Oh, would you like to?
I would like a mic. Thank you very much. Does this work? Okay. Okay, last but not least. So let me get started. Welcome, everybody. Thanks for coming. My name is Julia Gonski. I am a postdoctoral physicist working at Columbia University. Today, I'm going to tell you a story about our exploration of uncovered and unexpected phenomena in the fundamental particle physics world at the energy frontier. And I'm going to tell this through a kind of personal lens, my own particular story through the way that I got into this field, a couple of things that happened along the way, and the topics that I'm working on now. I need the clicker. Otherwise we'll be trapped here. Yes, so let me start by explaining what the energy frontier means to us as particle physicists. And at this moment in time, this is pretty much synonymous with the Large Hadron Collider. So you're looking here at a beautiful aerial shot over the French-Swiss border in Europe with the Alps in the background. And this red ring tells you where the Large Hadron Collider is, about 100 meters underground. So this is located at the CERN laboratory facility just outside of the city of Geneva, Switzerland. And what this ring does is accelerates protons. So we get them to really high energies, nearly the speed of light, and then we collide them with one another at dedicated interaction points along the ring. And what exists at those interaction points are particle detectors. So this image is an example of one of the 4 main detectors on the ring, the ATLAS detector. This is the one that I happen to work on. You can see this guy here for the scale of just how massive these machines are. And the reason that we have to build detectors around those interaction points is because we're extremely interested as high energy physicists in what happens in those collisions. So when you accelerate protons to this really high energy and you collide them, you're kind of rolling the universe's dice. Any number of things could happen as a result of that collision. You could produce new particles, you could produce particles that we know about already. All of those things spray off everywhere from the collision point, and we want to capture what happens. We want to measure all of the particles that come out and do this sort of forensics effort to figure out what happened in that collision. And that's because we're looking for the presence of particles that perhaps we haven't seen before.
And so the thing that the LHC is telling us is what particles could exist in these collisions, ones that we know about, ones that we don't. And to be able to distinguish between those two, I have to tell you about the standard model. So that's this nice periodic table looking thing that I'm showing you on the slide here. This is a table of all of the known fundamental particles and forces in the universe at the moment. This is the result of decades of theoretical work and experimental work, and it's a huge success, not only of particle physics, but I think science research in general. This is remarkably predictive of what we see in experiment. So it's a great model, but it's not perfect. You may be thinking about things that you know about in physics that are not included in this model just from glancing at it. Number one, gravity. So gravity definitely is a thing. We're all sitting here. There is no particle explanation for gravity at the moment, and there's no particle that carries the gravitational force. And there are a lot of results that are coming out of the field of gravitational research. I'll just cite one from the LIGO experiment that came out in 2020 that gave us evidence for the existence of gravitational waves, confirmation of general relativity from Einstein's theory of gravity. If everything has a fundamental particle nature, there should be a particle for this. And we would like to know what that is and have that included in the model. Another thing that we know definitely exists, definitely is a thing that is not in the model, dark matter. So when we look observationally at the universe, we know that there must be some particle that does not interact with the photon, but makes up nearly 80-ish% of the matter in the universe. This is a really nice image from the Dark Energy Survey showing the relative density of dark matter in the sky. So again, definitely exists, but we don't know the characteristics of that fundamental particle. And if our model was perfect, and we are indeed perfectionists, we would like to have a particle explanation for it. So this tells us that the standard model, while great, it's gotten us far, but it's not complete. And so we need the LHC to potentially produce the particles that make up this and a lot of other interesting phenomena in the universe. So a great example of this working well is the discovery of the newest particle in the standard model, which is the Higgs boson. So this principle of taking protons, accelerating them to really high energies, colliding them and seeing what happens, led us to this discovery of a particle in 2012. This was the last known predicted particle in the standard model. And so this was a massive achievement. It was nearly 50 years after it was first predicted in 1964 by this guy, Peter Higgs, and a couple other people. It won the Nobel Prize in 2013. This was an image from the CERN auditorium when this discovery was announced. So this was game-changing for the field of particle physics. This meant the standard model was nearly complete. This plot on the right, there's a lot going on here, but this is the money plot from the discovery. And what we're doing when we reconstruct that particle collision data is compare it to what we expect. So if you had only the standard model in your particle collision, you can make something like this red line. That's actually a signal post background, but you can compare the smoothly falling background from your standard model to the black data points, which tell you what's actually in the data. And a plot like this tells us that we have this new particle. It looks like the Higgs boson. It has a mass of 125 GeV, which is a fancy particle physics unit for mass. It means it's about 100 times the mass of the proton. And so this is where I came into the game of particle physics. I was an undergraduate at the time at a place called Rutgers University. Yeah, it's the State University of New Jersey, so we're loud by nature. And so here's a photo of me. The first time I went to CERN, it was 2013. I was a summer student. I was over the moon. I thought this was the coolest thing. I had actually just started working on Higgs physics. I was doing a Higgs to WW analysis, and about 4 weeks in, they found the thing. So you're welcome. You waited 50 years. You just had to get 20-year-old me to take a look at the data. So, but it was really formative for me. It got me completely hooked on the field. I wanted to keep looking at this data and keep seeing if there were any new particles out there. And I decided to go to graduate school and get a PhD to keep doing that. So a lot of time has passed since 2012. This is kind of a dated story. You're probably thinking that, there's a lot of really hardworking scientists, thousands of them on the most sophisticated experiment in the world. They've been up to really amazing stuff since then. And that's mostly true. There are mishaps along the way. So this is just a funny story from 2016. This cute little guy chewed through an electrical cable and took down the whole machine. And what I like about this article in particular is that the original quote says they believe the creature was a weasel, probably, and then updated it, indicates the creature may have been a martin. So attention to detail in physics. You really gotta pay attention to these things. But in reality, even though we haven't made any new discoveries since the Higgs boson, we have been hard at work. So in reality, what we've been doing is making a lot of plots that look like this. So this is a complicated plot. I'm just going to really highlight the key things to take away here, which is that the axes of this plot are masses of fancy new potential particles in that GeV unit that corresponded to the Higgs mass. And everywhere you look on this plot that is colored is a place where a particle cannot exist at that mass. Okay, there's a big asterisk there. Don't quote me on that. There's like statistical stuff that goes into it, 95% confidence. But the point is that we can use these null results to do better searches in the future. So if we're looking under a bunch of rocks for new particles, at least we can paint the rocks that we already looked under so that we don't just go continue to flip them over and over again. We are narrowing the number of rocks that we can look under and thus bringing us closer to the discovery of new physics. And to illustrate that point, I can show you how much colored shaded area we had excluded as of 2012 and how much more we have done in the decades since. So that's all bringing us closer to exactly what new physics must look like based on all this data analysis. And so then I'll note here that the orange part of this plot is my work. This is what I worked on, one of the things that I worked on as a PhD student. All the yellow parts are something that I actually touched, which is always nice to see. And as it turns out, they'll give you a PhD for this if you stick around for long enough. So here's me beaming, super excited. You can tell from this figure and the funny hats that it's a very dignified thing to get a PhD from Harvard. It's very glamorous. I would have to honestly it's a bit more honesty like this. It's a picture taken from the same day. And so apparently getting a PhD means that I thought that I could drink champagne in the middle of the day and eat like exclusively cookies for lunch. I was noticing this in this photo later. But this was, it was a really exciting thing. It was an exciting moment. And then I moved on to be a postdoc. So a research scientist with a PhD. Now at Columbia, I'll land on last couple notes of some things that I am working on now. And one of those is to introduce machine learning to LHC searches. So we have a huge amount of data that's coming out of the LHC, and we can take advantage of developments in computer science to do a better job mining that data for potential signals. So an example of this is to use a neural net to classify a potential new physics signal out of the background. So most of our problems reduce to something like signal to noise, where we're interested in one really tiny needle in a really big amount, a very large haystack, a huge amount of regular standard model background, things that we've already seen, so we don't need to continue to see them. And a neural net can take those two sets of objects, you as the user label them, you say this one's a needle, this one's hay, and it will build you a fancy classifier that separates those two things, such that if you're interested in needles, you can pull them out. And I will give you one more example of a cool application of machine learning that I've been really interested in lately, which is anomaly detection, where you don't necessarily label your inputs, you teach a classifier to learn what it has to learn to pull out anomalies. So with this, you can classify many types of new physics all at once. You don't need to separate needles from hay, you can separate a Hot Wheels car from hay. So I would be remiss if I didn't give you one new result to land on. This is something that my team just put out. It's the first application of fully unsupervised machine learning to the Atlas experiment. And if you Google this conf note, you can take a read of the paper. It's really interesting. And that's it. No negative numbers, though.
Bring out the chairs. So we have enough time for a few questions. Let's get all of our speakers out here. Let's get them comfortable at first. So, support team, get a mic.
Mike's here.
Come stand here where you can see who's raising their hand for a question. Ask whatever you like. Is there one already?
Brave soul in green.
Good. There's no way you're going to sit in a chair, is there?
I have my little thing. You guys don't have little things. Find a mic.
No.
Go ahead, in green.
Oh, you need here. Now you have a mic.
I have a question.
All right.
I thought you were wearing it.
Extracting
may not be
rare
on.
earth that is magnetic. Hello?
Yes.
Okay,
Man in
so
green.
we extract magnetically from sand, the rare earth.
I didn't catch it.
make
One more
an
time.
ingot out of it, send it to space,
Yeah.
and do
At
that.
$1 million a kilogram. Send it to space and then?
Then you have magnetism around the planet, and you can do all sorts of
Use
cool
the
shit.
mic.
Okay, thank you. Ladies and gentlemen, the man in green. So if I can repeat the question, I think the question was, if we take rare earth elements, we send them into space, say. It creates magnetism, perhaps. What kind of cool shit could you do with that? And you might not expect an answer from a crowd of, people talking about neutrinos, the X particle, and this is for you all. I shouldn't hold this. and all that. But, okay. So, you all know about the James Webb Space Telescope? Just nod your head, everyone's okay. So I'm at I got to teach physics, just level with you here. I'm at a physics teacher conference, as boring as, it's a great conference, don't get me wrong, but it's a physics teacher conference, and the one thing we don't do at physics teacher conferences is physics. And as a physicist, that kind of annoys me. So I start talking to some students. I say, hey, what's going on? What's new? What's happening? And they say, hey, we're trying to learn about this thing. Okay. So we're looking at the speaker. Speaker's talking about the James Webb Space Telescope. James Webb Space Telescope. They have no data. Now we have particle physicists. We have experimental particle physicists. You don't give a talk if you don't have data. You don't even send an abstract if you don't have data. You need data. This guy, he's showing a picture of the people who put the telescope together. He's showing a trip he took to Hawaii. I'm like, I lose it. I say, hey, give me 4 of these high school students. We're gonna go outside. We're gonna take 10 minutes while this guy finishes this, whatever he's doing. And we're gonna find a way to use the James Webb Space Telescope in space, using magnets, to figure out what 85% of the matter in the universe is. You feel me? I love neutrinos. I love the Standard Model. Our calculation that I'm about to reveal to you is based on the Standard Model, neutrinos and all. Mainly just the number of them. There's 12 of them, the detail. We took 9 minutes and we found an answer. The biggest source of magnetism in the solar system is not rare earth elements that we shoot up with Elon Musk and his buddies. I didn't mean to disappoint you. You're expecting that. The biggest source of magnetism in the solar system is the sun. The sun. Okay. Unfortunately, James Webb Space Telescope was designed by Raytheon Corporation's engineers to have its back to the sun, as you do. And you may have heard about it. They had these minutes of terror. They were waiting for the heat shield to deploy. Now it's deployed, and they never look at the sun. Okay. That was minute 3. We were talking, some high school students tonight. Okay. So you can't look at the sun, the brightest, biggest source of magnetism in the solar system. What if we looked exactly opposite? The sun's magnetic field doesn't stop at the Earth. It doesn't stop at the sun. It keeps going to interstellar space. It's not a big field. We don't need it to be big. We use these crazy units. They're called milliliters, centimeters cubed. It's 10 drops. 10 drops, a billion. 10 drops, a billion dark matter particles. Just chilling since the Big Bang, waiting for a solar magnetic field of a certain size to just be there. Meanwhile, the James Webb Space Telescope, for various reasons having to do with funding and whatever, resonates at exactly the dark matter frequency that you get from this number 12, the number of particles in the Standard Model. We turn our back to the sun, we follow the magnetic field. When you turn the detector this way, you see the dark matter. When you turn it that way, you don't. That, I believe, is the answer to your question.
Next question, please.
You in the front.
Hi, can you guys hear me? Yeah, no? Good, okay. So this is a question for Jorge. So if we're looking for neutrinos, what kind of information, do we know what kind of information they could carry so that we use them? Like, how would they be useful?
Yeah, that's a good question. So you're talking about the specific example I give or in general?
In general, because you're saying if we're able to catch them, like, I just want to know what can we be able to deduce from them?
Yeah. So there are many things that we don't know about neutrinos. One of them is their mass. We don't know the exact mass that they have. We know that there are 3 different kinds of types of neutrinos, but we don't know their masses. We know the sum of their masses, or we have a limit for the sum of their masses. So detecting them, we can learn such things. We can learn what their masses are, we can learn things, whether they are their own antiparticle or not, because neutrinos are neutral, and if you cannot distinguish between particle and antiparticle because it had the same charge or no charge, right? So we might be able to also learn whether they are their own antiparticle or not. And then other things, now, if we observe neutrinos that come from space, we can learn what processes are fueling this very violent galactic or extragalactic astrophysical sources. So, we have these things that are called pulsars that emit a bunch of things. And sometimes I don't think we know what's going on inside there. Photons cannot come out, or the ones that come out, they get stopped. So neutrinos can tell us more information about what's going on in there. Yeah.
I have two follow-ups to that, what Jorge just said. First of all, our sun emits neutrinos through nuclear reactions, but it only emits electron-type neutrinos. But whenever we measure neutrinos here on Earth that are coming from the sun, we measure all three kinds of neutrinos. We see some that are electron type, some that are muon type, and some that are tau type. Our science up to now shows that this is in good agreement with a model that the electron neutrinos, as they're propagating through space, they oscillate into these other kinds of neutrino. So those studies of neutrino oscillation, those have revolutionized the standard model. That wasn't part of the standard model of particle physics that would happen. Another thing you mentioned, pulsars. A friend of mine does theory around neutron stars. And a fun thing about neutron stars is that they lose almost all of their energy. They cool by these neutrino winds. Like our sun emits light and that pushes energy away. Neutron stars, they're trying to collapse under the force of their own gravity. But what's actually holding them out is this wave of neutrinos that's flowing out. And various other processes are all producing neutrinos in space. And hopefully we can actually measure some of that and get information about these astrophysical objects and the fundamental physics that's going on inside of them, which is really cool.
Thank you. Next question, please.
So in the data plot for the Higgs data that got the Nobel Prize, I'd never really noticed how nicely the curve looks. It has a nice little bump, but the actual data points, it's not very convincing bump there. It looks like it kind of just keeps on going. I was kind of like, that doesn't look very convincing to me, So.
Yeah, I think I've heard that before, and there are some other particle discovery plots where you look at it with your human eyes and you're like, are those data points really in excess of the background? Like you really can't even tell. We do so much statistics, it would make your head hurt. So in the end, the way that we develop confidence, what we label as a discovery, is using sigma significance. So we do a lot of hypothesis testing. This is what I think that my standard model background would be. This is what my signal would be. And you test them against one another and see if you can get a 5 sigma deviation of the data from the background hypothesis, 5 sigma significance for the signal plus background hypothesis. And all those things relate to the computation of your background model and the errors on the statistical errors on all these elements that go into it. So it is a very complicated procedure, but I think the point I'm trying to make is that it's harmonized for every single discovery. There is an objectivity to the way that we decide, okay, this is significant enough. We have found it, it's discovered. It visually looks different, very much case by case.
And the actual number of data points would be much larger than what was on that graph, right? Because there's only a handful.
Yeah, the Higgs discovery was only made with a handful of events. Since then, we've produced, I don't know the exact number, but we've produced, so many more Higgses, and by adding more data, you can lower the statistical uncertainty, and that gives you more confidence in the hypothesis that you've built. But you can make a discovery with a relatively small number of events. It just depends on what's on the background side, and that gives you the confidence in the hypothesis testing. Yeah.
One more burning question.
That's a burning question.
Hello. I have a question for Professor Gray. When you were talking about dark matter, I got kind of confused because you mentioned the right and left-handedness, I'm guessing, of the universe, And I'm just trying to ask what kind of particle interaction or mechanism you're trying to describe with the analogy as the symmetry for dark matter.
It's a symmetry argument. And yeah,
Yes.
That's
it-
great.
Professor Gray and Professor Bray.
Oh,
So-
sorry. My mistake.
So it's a symmetry argument. And the way symmetry arguments go is you start with the answer and you find the right symmetry. Okay. So a moment ago, we heard from Julia about sigmas. And in our field, 5 sigma is when we start giving ourselves prizes. Last April, not last April, April but one, April 2021, we're still in the lockdown, and I get an email. One of my former students, I'm like, oh no, I gotta write another letter. I mean, wow, I get to write another letter. And I open it up and I'm shocked, disappointed. I don't have to write another letter. He says, Professor Bray Ali, well, he called me Noah. Professor Noah, he calls me Noah. Noah, why are 10,000 people tuned into a YouTube live stream from the largest particle physics experiment in North America? Of course, Julia's is bigger, but it has the effect of being European. So America is always trying to get back on top. And in April 2021, 10,000 people, including me, I don't know, but I'm going to tune in. I tune in. They found an event that's 4.2 sigma. 4.2 sigma, if you're in the back. 4.2 sigma. 4.2 sigma. I'm like, what's a sigma? I don't really do particle physics, it turns out. So, you know, I'm with you, okay. So I look at him, listen, and the guy who's on stage, his buddy, not him, but his buddy comes to my university, or the one next door, and he's giving like a talk, and it's all on Zoom, so I'm checked in. I say, hey, professor, what's a sigma? What's the statistics and all that? And he says, you know, the answer, and I say, hey, wait a second. 20 years ago, I was an undergraduate. And my boss at the time had a crazy idea. He said, hey, you want to work on this for your whatever so you can graduate? I'm like, that sounds like that's not going to be solved before I need to graduate. Give me the computer programming. I'll just do the tickety-tackety and get my degree and go. I'm not trying to stay around and solve physics problems. I call that guy up. He replies. He's kind of air professor, doctor. Yes, I remember you very well, Noah. 20 years ago to the day is when I signed the papers that you could be out of my control and go into the real world. But why are you emailing me? I say, what about that crazy idea you had, man? He's like, yeah. You think it could be? I said, yeah. He says, okay, but you do the work. I said, okay, well, who gets the credit? He said, we'll split it if it works. So I email him. We start thinking, and pretty soon, the sigmas, they start to fall into place. And the symmetry starts coming to mind. So what's the symmetry? And what's the argument? What's the interaction? Okay. They have a ring. And they know how to use it. They put a particle in there and it goes this way. Okay. Then they get the negative version of that particle and they have it go the other way. And it switches by 5 sigma. They don't publish it, but it switches by 5 sigma with 28 days of running. Right now, to keep the theorists happy or whatever, to make it all sciencey, they just compared the one that goes like this to some theory calculation, and it's only 4.2 sigma, and it's got all these uncertainties. But if they just do it the other way, rather than being high, they get low. And so I said, oh, it must have something to do with time reversal, because that's the only thing that's different. Right? But it turns out if you do the
This story is getting long.
matter antimatter,
We gotta get
you get the end.
anyway, and
in the
then
hook. And so it turns out the particle that makes up 85% of the mass of the universe is the particle that this professor has been looking for 30 years. We went to the bar last night.
I'm not 30 years.
We went to the bar last night, Professor Gray and Professor Bray. We drop our keys at the bar, you feel me? And I asked Professor Bray, what should we do? He says, I don't know, but I have a very well-tuned radio frequency cavity in my lab. Let's go look there. We go, the bartender comes out, he says, Professor Gray, the Axion was found at Fermilab in April 2021. What are you guys looking for in the radio frequency? It has a mass in the infrared. And so the interaction we look
I don't
for is
remember
the
this
same
at
way.
all.
the same one that Professor Gray's been trying to look for, is one piece of dark matter becomes 2 photons. So,
All right. That is
Thank
all
you.
the time we have for questions, I'm afraid. So the time has come. I need an arbiter. Who is a UW physics undergraduate?
what do you smoke?
Okay,
What do you
so
You're live, you're hot.
you've taken your lab courses? You've taken your lab courses. You're going to read the instrument. These people are going to be busy clapping. All right. So, judge on entertainment, on science, on whatever metric you choose. But give it up for, I'm calling you Noah. You can be Professor Bray. That's okay. Noah, give it up for him. Now let's hear it for Jorge. My favorite, the local, Heather. Julia. The Jersey advantage. The Jersey advantage on the sound meter. So,
Professor Gray.
who was it? You've been calculating? Your error bars on that?
So while they're calculating,
All right. 1 moment, please.
if I may have mentioned that we do all this for you. And this is the time when we ask our ask. You heard today stories about
Fabulous prizes. We're promised.
fabulous,
Nick, come on.
about the
Oh
largest
my God.
scientific
story
machine in the
again.
world, about neutrinos. We need you to work on these projects. That's why we're here today. So
Oh,
think
sure.
about these projects and ask yourself, what can I do for Professor Gray, for Julia, for Jorge, and for Heather?
You have won a cup.
Thank you so much.
What?
You have won a cup. You have won a cup. We're loudest for Jorge, so Jorge gets a t-shirt.
Nice.
Thank you very much, everybody. You've been a lovely audience. We've had some lovely speakers. I hope to see you here sometime again soon. Bye.